Hello everyone, I'm Andrea Possemato and I'm a PhD student at Eurocom. Today I'm going to present you our work Trust But Verify, a longitudinal analysis of Android OEM compliance and customization. Nowadays, the Android ecosystem consists of more than 1,300 different vendors that build more than 24,000 different devices. However, some of the customization made by the vendors may also introduce vulnerabilities at the source code level, or may also lower down the security of the entire device, where changing, for example, sensitive configuration file used to build native libraries of the kernel component. In order to avoid that these dangerous customization take place, Google started to introduce a set of rules to follow. The first set of rules takes the name of compatibility definition document. This document is published for every new version of Android, and basically states what the vendor must do, what the vendor must never do, and what the vendor should do or is strongly recommended to do when dealing with the customization of the system. The second set of guidelines takes the name of a security enhancement. The security enhancement basically lists all the security features and tools that are at the disposal of the vendor when dealing with the customization of the system. Compatibility definition documents are a set of rules that are written in a natural language. As we can see here for Android 8, the compatibility definition document states that all the kernel must implement stack buffer for protection mechanism. And this means that vendor, if they want to target Android 8, they must configure their kernel in this specific configuration. If we look for the security enhancement, however, we can see that on top of the rule that the vendor must follow, the vendor can also decide to adopt other hardening features, for example, KLSLR. In this paper, we want to investigate whether vendor actually respect these rules. To perform this investigation, however, we must first understand how normally a vendor modify an Android image. Everything starts from the original chip manufacturer that from now on we will call the vendor that fork or clone a specific version and a specific release branch from the Android open source project. As we can see, for a specific Android version, for example, the version 9, there might be several release branches. Once the code base is ready, then the customization may take place. As we saw before, customization may take place in several layers, starting from the kernel to the system app down to device driver. Moreover, the vendor can also modify initialization script, SE/Linux policy, and everything that relates to the graphical user interface. When the system is fully customized and ready to be shipped on the device, then the vendor can also decide to perform a set of testing that takes the name of compatibility test suite and vendor test suite. At this point, we also want to thank Google for an important clarification that at this stage, only compatibility test suite are mandatory for a vendor. And we wrote that also vendor test suite were needed, but we thank Google for this clarification. When compatibility test suite are done, if they are completely passed, then the vendor can also be branded as Android compatible device and may also be equipped with the Google mobile services. This means all the mobile application developed by Google, starting from Gmail to the Google Play Store. Otherwise, if the compatibility test suite are not passed, then the device might not be branded as Android compatible device. So once we know how the customization normally takes place, then we can also start hunting for this customization to understand whether or not they respect this rule. To perform this analysis, we decide to build a pipeline that takes an input system image in the form of an archive. Normally in this archive, we have all the file system that will be flashed on the system. Once we unpack the archive, then we can mount all the file system, and at this stage, we will have access to all the file that will be flashed on the device. So at this stage, we can perform all the extraction of the data and the feature that we want to analyze. And for this specific research, we want to focus on a subset of levels that the vendor normally modify. So for our research, we decided to analyze the kernel modification, SE/Linux policy, init script, and the executable in the form of binaries and libraries. At this stage, it is also important to identify the correct Android base image that was used by the vendor, so to extract the correct version and the correct release branch. After that, all the data extraction phase is done, we have our own profile. So we have all the features that characterize a system image modified by the vendor. Then, since we were able to identify correctly the Android version and the Android release branch, we can perform the same initial stage of the vendor. So we clone and compile the Android open source project, and we extract the same data that we extracted from the system image. So at this stage, we will also have the original profile of the Android open source image. These two profiles will then allow us to perform two complementary analyses. The first one relates to compliance. This means that we take the ROM profile and we analyze if it respects all the rules defined in the compatibility definition document, but also a customization analysis. This means that if we have both the original profile and the profile modified by the vendor, then we can check by comparing them if the customization made by the vendor are in line with the security line of the Android open source project, or if they are all lowering down the overall security of the system. We used this pipeline to analyze more than 2,900 different system images, all of which are configured with the Google Mobile Services. So in theory, they should have passed compatibility test suite. Our dataset dates back from 2009 with the oldest Android version of 1.6 up to Android 9, the latest version that we have dates to 2020. In total, we analyze system images from 42 different vendors. So let's now see how we verify the compliance. We decided to focus our attention on the compliance analysis for three specific layers: the kernel, the SE/Linux policies, and the binary hardening. For the sake of time now, we will only analyze what we did for the kernel, but please keep in mind that also the analysis for SE/Linux policy and binary hardening are completely different analyses. And if you want to see all the detailed results for this analysis, please refer to the paper. So as we saw before, we have access to the system image from the vendor. Within the system image, we have the kernel binary. And as we saw before for the compatibility definition documents, the master rule defines a set of configuration the configuration flags that must be adopted by the vendor. This means that we have to extract all the configuration used by the vendor when configuring the kernel, but at this stage, we also decide to extract the symbols. We extract both of them because there is a direct mapping between configuration and symbols. And this means that if we are lacking of the symbols, we can go back to the configuration and vice versa. So we are trying to extract as much information as possible. Once we have a list of configuration that the vendor used when configuring the kernel, we can start the compliance analysis. So we take the kernel, we take the configuration file, we take the version of Android, we take the corresponding compatibility definition document, and we check if the kernel actually respects all the rules that are defined as must, and also if the kernel implements any of the rules that are defined as strongly recommended on the compatibility definition document for the specific version of Android. However, our results show that even with the compatibility definition document, still 8% of the kernel violated the compatibility definition document. And the most common violation that we found on 150 kernel actually relates to the missing of these two configuration flags that marks a sensitive memory region as read-only in the kernel, for example. So we saw that 8% of the kernel binaries, they do not respect the compatibility definition document. But we also see that for what concern the SE/Linux policy, we still see 29% of the policies that are not in line with this set of rules. Please keep in mind that at this stage, we analyze a policy that is retrieved from a static firmware and not from a running device. And this might slightly change the result if you repeat the same analysis on a policy extracted from a device. And also for what concerns the binaries, we saw that roughly 3% of the ROM that we analyze actually have some violation for what concerns the kernel binary, the binary hardening feature. So after having analyzed the compliance of the modification made by the vendor, so we also wanted to focus on understanding how dangerous they are. And so we decided to focus at this stage on analyzing how the customization takes place and what are the net effects on the security of the system. We decided to analyze the perils of a customization for what concerns the user space binaries, the SE/Linux policies, and the initialization script used by the Android system. The same for the compliance. For the sake of time now, we will only see the user space binaries. If you want to see all the details for the remaining part of the analysis, please refer to the paper. To analyze the customization of the binaries, we decided to adopt two complementary approach. The first one is a differential analysis. Since we have both the profile of the system and the Android open source project, then we can extract all the common elves that are shared between the two images. At this stage, when we have both the common elves that are basically in the same location of the file system, we can start hunting for modification. The first type of modification we want to analyze relates to the modification of the binaries, for example, if some function are added or removed, but also very interesting to see how these binaries were modified in terms of hardening compilation features used by the vendor. Once the differential analysis is done, then we can perform an additional customization analysis, where this time we only focus on the new executable libraries that are added by the vendor. And we decide to focus our attention only on the analysis of the hardening compiler option at this stage. So let's now see the binary customization analysis for what concerns the modification of the shared libraries and executables. As you can see on the top part of the graph, we have the mean of percentage of shared library that are modified by the vendors, while the lower part of the graph shows the mean number of new functions that are introduced in a shared libraries. As we can see, starting from roughly Android 15, there is this almost constant trend of roughly 80 new functions added to 20% of the system libraries. This is particularly bad for what concerns the application of the patch, because modifying shared libraries might make the application of the patching not automatized, and also might increase the time of which these patches are ported to the system. An additional analysis that we perform on the compiler mitigation shows on the left the results that we extracted from the Android open source project, while on the right, on the green side, the results that we extracted from the vendor binaries. As we can see, vendors significantly lag behind with respect to the Android open source project when dealing with the compiler mitigation. Roughly starting from Android 23-24, we can see how the binaries in Android open source project completely enable security mitigation like stack canaries, not executable stack, and Furtlerlo, while vendors do not yet adopt all the mitigation that are provided by compilers, unlike Android open source project. So to sum up the result of this analysis on the customization, we saw that for the binaries, there is this constant trend of system libraries modification, and we also saw how vendor use deprecated function, probably due to legacy code. The analysis on the Linux policy showed that this trend of aggressive modification actually is valid also for this analysis here. We saw how vendor aggressively modified default policy. We identified some of the vendor having policies that are 20 times bigger than the original one offered by the Android open source project. And we believe that this growing number of customization might have the risk of having over-privileged rule, which of course open security issues in the system. And last, for what concerns the script, we saw that this trend is valid also for this component. We saw a vendor considerably change initialization script to start always growing number of overprivileged services. We also identified that there might be several security and repercussion issues for the end device and for the end user. For example, for 18 images that we analyzed, we identified how the ROM configured services to start at the boot of the system. At the boot of the system, the vendor was starting TCP dump. TCP dump is particularly bad because it was listening in for all the interfaces exposed by the device, which opens, of course, a problem for the privacy, because all the network traffic that is read by TCP dump then can be exfiltrated, but also we analyzed how this might also add a security issue, because for some of these ROM, we identify how the version of TCP dump was updated with public CVEs, and also public proof of concept were available. We were able to test one particular version of TCP dump with the public proof of concept, and we were able actually to replicate the crash. So to conclude, we perform a longitudinal large-scale analysis of more than 2,900 different ROM. We found that many certified ROM actually do not meet the prerequisites that are defined in the compatibility definition document, and so they are not compliant. And also we saw how specifically vendor-specific components significantly lag behind with respect to the security posture of the main Android open source project, highlighting how this customization normally relates to the lack of compiler mitigation or the configuration of overprivileged services and Linux policy. Thank you very much for your attention. If you have any question, please feel free to ask. Thanks.